Assalamu alaikum, guys. Today, the topic of our lecture is frequency domain representation. So, the topic is frequency domain representation of a signal. Of signals. Of signal. So, in this topic, we will actually give you some idea about how a time variant signal can be expressed in frequency domain, right? Or time domain signal can be expressed in frequency domain signal. These topics will be more elaborated in your signals and system course. So let me see how far I can explain you this topic. So this frequency domain representation is actually a fundamental tool for communication. So this is actually one of the very much fundamental tool for fundamental tool for communication system. Because this topic is more applicable for analog communication. In this case, usually analog signals are usually represented in time domain, but it has a significance also for its representation in frequency domain also. So when a signal or time domain signal is actually expressed in a frequency domain signal, it is called actually a spectrum of a signal. So when it is in frequency domain, we call it spectrum of signal or signal spectrum. This spectrum of the signal spectrum can be actually divided into two parts. One part we can call it Fourier series. Fourier series. Other part is called Fourier transform. In your signals and system course, you will actually would get the detailed idea of both of them. For the purpose of analog communication, only Fourier series will actually be considered. Okay, so this is actually the Fourier series will be expressed discrete in frequency. They are actually expressed discrete. Fourier series actually discrete in frequency. And the Fourier transform is actually continuous in frequency. Continuous in frequency. And this discrete frequencies are defined for a periodic signal. So it is actually defined for a periodic signal. Whereas this continuous in frequency is actually for non-periodic signal. It's actually expressed for the non-periodic signal. But for the sake of this course, will not further go for this Fourier transform, this part, okay? So this is actually no-go zone for us. We are not that much bothered about Fourier transform. We will be only bothered for the Fourier series, which actually discrete in frequency because it defines for a periodic signal. Because the analog communication we will be discussing, they are fundamentally a periodic signal. Okay, so let us consider a periodic signal. So consider, because it is for analog communication, so consider a periodic signal. with period t. So this signal is xt. Let us consider signal xt. So if this is the signal xt, the Fourier series of xt, so the Fourier series is given for xt is, so we can express it as xt equal to minus infinity to plus infinity ck e to the power j 2 pi k f0 t. Here f0 is nothing but 1 by t, which is actually this f0 is the fundamental frequency of the periodic signal. This is actually fundamental frequency of the periodic signal xt, right? This signal. And ck here, ck is the kth discrete Fourier series coefficient. Fourier series coefficient. So we expressed a Fourier series of a periodic signal, which is actually xt in our case, by this equation, where we define these two parameter. This f0, k is the kth, that's why ck. We are considering a kth signal, which is actually an arbitrary signal. Okay. Okay. Now, what is this amount? E to the power j 2 pi k f0 t. This is, so e to the power j 2 pi k f0 t is nothing but, so here I will actually request you to recall an old formula called Euler's formula. Euler's formula. Where we actually expressed a real and imaginary part of a signal or of any component. Here, this is actually e to the power j theta. This angle is theta. Here, the x-axis corresponds to the real part, and y corresponds to the imaginary part of this e. This e. Okay, and here this is the cos theta part, and this is the sin theta part. So e to the power j theta, is expressed as cos. So we know e to the power j theta is nothing but the cos theta plus j sin theta. This component and this component. This is imaginary. This part is imaginary. That's why this j comes. Okay, same thing. So we actually express e to the power as j theta, this part. So cos theta is twice pi kf0 t plus j sin theta, right? Sin twice pi kf0 t, which is, so this part is the complex sinusoids. So this actually a complex sinusoid, huh? Complex. So this actually much useful in analog communication, where we actually express a signal in complex form. This form. So we are expressing our signal in a complex, where this kf0, this kf0, what is this kf0? Kf0 is the multiple of the fundamental frequency f0, right? So this is k is a variable, eh? The k is a value, probably k value is 0 to up to n, right? So it's actually nothing but the multiple of fundamental. So this f0 is the fundamental frequency, multiple of fundamental frequency f0. Okay. So if this is the case, then this amount k equal to minus infinity to infinity ck. Okay, so here actually I didn't write this one, k equal to, that's actually this value of k. K varies from minus infinity to for all the values. So the fundamental, after the fundamental frequency, it can be, values can be any, either positive or negative up to n value, minus infinity to plus infinity. Actually here this actually k is not this value, so k is actually minus infinity to plus infinity, all the values in positive and negative. Okay, so this is a infinity. So these are one k ck e to the power. What this expresses actually? Here we see, here in this example, this amount is nothing but the complex sinusoids, and ck is a discrete Fourier series coefficient for the kth value. So this amount ck, so this value ck e to the power j twice pi k f0 t, where f0 is a fundamental frequency, is a linear combination of summation of various complex sinusoids in a either frequency of f0 or kf0. Okay, so what this actually mean? So these equation mean what? Whenever we have a periodic signal xt, which we actually express in a Fourier series, what does it mean? So this, it means that this expression is a linear combination or summation, because this is a summation. So this is a linear combination of all the complex sinusoids. If you vary k from any value to any value, for example, if you vary from vary k from 0 to plus infinity, so this k and this k would keep changing, and they are actually the complex sinusoid, right? Individually, and you have a summation here, summation. So this is actually a linear combination or summation of various complex sinusoids. In either frequency f0 or kf0. Either it's fundamentals or multiple of fundamental frequency kf0, multiple of fundamental frequency. Where kf0 is, where kf0 is multiple of fundamental frequency f0, where kf0 is multiple of fundamental frequency f0. So we can conclude that if a periodic signal is xt, or any periodic signal is a linear combination of various complex sinusoids, either fundamentals or multiple of fundamentals of F0 or its harmonic. These various frequencies, we can call it harmonic. So a periodic signal is nothing but the combination or linear combination or linear summation of its multiple of fundamentals, okay, or harmonics. So every periodic signal xt with period of like fundamental frequency F0 is a linear combination of infinite number of sinusoids at fundamental frequency F0 or its integer multiplication of F0. That's actually we are trying to say for this equation. This equation. This one. So we are saying that every periodic signal, because this is also this is actually xt. So every periodic signal xt with period of fundamental F0 is a linear combination of infinite number of, because k goes from minus infinity to plus infinity, so it's infinite number of sinusoids because it's a sinusoid or complex sinusoids at fundamental frequency F0 or kf0 or its integer multiplication. Okay, now we can say that e to the power j 2 pi kf0 t is the kth harmonic. It's actually the kth harmonic. Because periodic signal is a combination or linear summation of complex conjugate of its harmonics. Harmonics means fundamental plus any other higher frequencies or any other components. They are called fundamentals. Harmonics. So we can express this is because this is k, so this is kth harmonics, which is actually because k varies from minus infinity to plus infinity, means actually it's all the harmonics. Okay, so ck is we already know that ck is nothing but the coefficient of the kth harmonic. So ck is the coefficient of kth harmonics. So any periodic signal can be expressed by its harmonics. That's actually a very simple definition of Fourier series. Okay, if you express any periodic signal by summation of its harmonics, then actually it's called a Fourier series. That's actually very fundamental stuff. For example, if you have a signal of xt, it's nothing but the harmonics of its x1 plus x2 plus x3, like this, blah blah blah, blah up to infinite values that we are seeing. So now we'll actually look into the coefficient ck of discrete Fourier series. So we actually look into the coefficient ck. We actually look onto this one. So the coefficient ck of this discrete Fourier series because we actually already defined that we are expressing a Fourier series which is actually discrete in nature because this is for a periodic signal. So this is actually a discrete Fourier series. It's for a discrete Fourier series because this is actually a discrete xt actually is expressed in a discrete Fourier series. So ck is also a coefficient because every ck is a part of this one, right? This harmonics. So ck is a discrete Fourier series. So ck is the coefficient of the discrete Fourier series, right? So okay. So for a specific coefficient, okay. So this k value is minus infinity to plus infinity. So we like to know about a specific coefficient. So imagine for a specific coefficient. So let give it a name. So it's a specific. So let it give it a name L. Okay. So this k is variable, minus infinity to plus infinity. But this L is a fixed one. For example, is 5th or 10th or 20th of coefficient, 20th harmonic, coefficient of the 20th harmonic. Okay, so it's a fixed value. So this can be this CL can be expressed at 1 by T. So this is for a fixed time period because this is fixed, particular for a particular harmonics. So minus T by 2 to plus T by 2 for a fixed duration or over a period. Okay, xt e to the power minus j twice by L f0t and dt. Okay, so here why we took minus from minus T by 2 to plus T by 2, because this integral is over one period. So this integral is over one period, one complete period, a complete cycle, one period. Because this is specific, this is not arbitrary for a particular harmonics. Okay, this is a coefficient for a particular harmonics. Okay, so we can express or we can rewrite it as 1 by t. This xt, we know the value of xt, right? So we'll put it the value. So minus t by 2 to t by 2. So we'll replace this xt value from here, which is actually equivalent to this one, this value, or this is the value for us. Okay, we already used it earlier, which is nothing but the xt is nothing but k equal to minus infinity, so minus infinity to plus infinity, ck e to the power j 2 pi k f0 t, which is actually this one, and this part also here, e to the power minus j 2 pi L f0 t dt. Okay, so we'll do some solution here. So this is actually so so what we'll do, we'll actually interchange the order of summation and integration. So here in this equation, you see there is an integration and summation. So we will actually interchange, interchange order of integration and summation, because integration is first, then comes summation. Integration and summation. We'll change their order. So they will look like, so I take it out, k equal to minus infinity to plus infinity, ck coefficient also out. So 1 by t, I put this integral inside. So minus t by 2 to plus t by 2 e to the power j. So there is two e value here. So e to the j twice pi k minus L, we can write it. Okay, f0 t dt, because these are the e components, so they can be simply have summation because of this negative this negative one. So here we have minus L. Okay, so now let us solve only this part. We like to solve this part for only this part only. Okay, this part only. Solution of this part will give us some idea about the property of this integral. So we'll try to solve this, the property. Let us find. So let us find the property of this, the of this integral. Okay, so here is the solution. We are solving only this part. Okay, so which is actually 1 by, like it's from here, so 1 by t minus t by 2 to plus t by 2 e to the power j twice pi k minus L f0 t dt. Let's have a solution for this. So if here, if two condition, if k equal to L, what happen in this equation? K and L are equal. What happen? K minus L becomes 0. So e to the power 0 becomes 1. So the solution comes as 1 by t minus t by 2 to t by 2 e to the power. It becomes 0. So e to the power 0 is 1 dt. Because it's 1 by t now, because 1 we will actually put t by 2 minus t by 2, which is actually plus t by 2, which is actually nothing but t. So we can actually cross it. It's actually 1. Okay, so this solution is 1 if k equal to 1 L. So if k not equal to L, what happens then? If k not equal to L, then what the equation comes as 1 by t minus t by 2 to t by 2 e to the power. So j 2 pi k minus L is 0 t dt. Now we have to solve this part. Oh, so what is the solution? So this will be, say 1 by t is okay. So we will do the integration. So e to the power x equal to e to the power x actually. So e to the power j 2 pi k minus L is 0 t. But this is not e to the power x. Okay. So we'll give the punishment. So which is actually j 2 pi k minus L f0, because this is d by dt of in respect of t, so which will be 1. So we actually put from t by 2 minus t by 2. So this is actually your elementary integration. We know e to the power, if we do d by dx, e to the power x actually e to the power x. But if we have d by d, like differential d by dx of e to the power minus x, then what happens? It's actually nothing but e to the power dx actually e to the power x, which is actually minus x. And now we have to give punishment d by dx of minus this minus x, which is like this is the way we actually do the solution. Anyway, I'm not going for a detail. Okay, so what we can write? So 1 by t 1 by j 2 pi k minus L f0. This part here, and here we actually e to the power, say e to the power j 2 pi k minus L. Okay. Okay. Here we already know from previous definition that f0 is nothing but 1 by t, and for t equal to 1, so f0 we know f0 is 1 by t. Okay. So f0 is 1 by t. Now if we do this, t by 2 minus t by 2 will be actually nothing but t by 2. Okay, where we can cross 2 2 and t minus. So this is for the upper part. For the lower part, so which is actually minus for the value of t by 2. For this part is this one. For this part we can write e to the power j 2 pi k minus L. So f0 is nothing but 1 by t, and into minus t by 2, right? So these two can be cancelled. This t and this t can be cancelled, and this minus comes in front. Okay, so what we can write, 1 by t 1 by j 2 pi k minus l f0. Here it will write e to the power j pi k minus l, right? Minus e to the power, you see this minus, this comes earlier, so minus j pi k minus l, right? Okay. Now here we can see this is a complex sinusoid, right? So this is also a complex sinusoid. This is also a complex sinusoid. So what is the phase difference between them? So we can see. So actually, this is a actually both of them are complex. So each of this is a complex sinusoid. So we can write there. We know that each of these these exponents or this equation, this is a complex sinusoid. Sinusoid, complex sinusoid. So they are actually equal. So they are equal, but with opposite phase. So the phase difference will be, you see, this is minus. This is E, which have a minus J. So they have a opposite. They have a opposite phase. So actually, the phase difference of these two are actually nothing but pi k minus l. Okay. Or actually twice pi. They are actually in orthogonal, so they will be, so which is actually a 0. For example, we know e to the power j theta, for example. E to the power j theta is cos theta plus j sin theta, and e to the power minus j theta, which is actually this value, which is actually cos theta minus j sin theta. So if you subtract, so there will be twice pi k minus l. This will be their phase, and that phase difference will be in 0. Okay. Okay. So in summary, so if we do in summary, so if I summarize this result, in summary, so what we can write in summary, we can write that in summary, we can write that if k not equal to l, one by t minus t by 2, 2t by 2t by j 2 pi k minus l f0 t dt is actually 0, right? This is actually, we find it from here. This is 0 because when k not equal to l. So this, if this is not k not equal to n, then this value becomes 0. Okay. So this is, so we can write actually, I can write that there are two condition comes, right? So 1 by t minus t by 2. So this is the whole summary. This is the whole summary, t by 2 e to the power j 2 pi k minus L F0 t dt. This value will be 1 when value is 1. Okay, value is 1 for k equal to L. 1 for k equal to L, and this value is 0 for k not equal to L. So that's actually the final summary for this part. So what we can say that e to the power j 2 pi k f0 t and e to the power j 2 pi L f0 t. See, we have two. Here, e to the power k j 2 pi k. If it's k, means it can be any arbitrary value from minus infinity to plus infinity. But this is a specific for Lth harmonics. So, means if any Lth harmonics or any different harmonics, they are orthogonal. Means actually we are comparing. I'm comparing a specific harmonics with any arbitrary harmonics, right? Means they are two different harmonics. So what we can say, different harmonic harmonic are orthogonal. We actually already seen if they are not equal, their value, the product of this value is 0. Dot product is 0. What is an orthogonal? So we know from definition the two signal x and y, they are orthogonal, means their dot product is 0. So dot product is 0. Okay. So any signal x and y, for example, any signal x and y, for example, if we would have been writing it this way, for 1 by t minus t by 2 to plus t by 2, means whole period is considered a signal xt is dot product with a yt, or actually the complex conjugate of yt dt. If we integrate them, their value will be 0. That actually it means that these two signals x and y are orthogonal, means their dot product are 0. That's actually we are trying to say. Yeah. So if you for example, if you replace this xt by this e to the power j k f0 and y is, for example, if it's 1 by t minus t by 2 to t by 2, and this xt is nothing but e to the power j 2 pi k f0 t, and this y is e to the power j twice pi L specific L f0 t dt. If you do complex conjugate of this signal or dot product this signal, their value will be 0. That's actually mean by orthogonal. Okay. So they are actually mean orthogonal. That's actually the definition of orthogonality, right? Means the kth and lth harmonics are orthogonal. Harmonics are orthogonal. Okay, so we find the definition of this orthogonality. So now we will find so we find everything. You see, we actually find the value of this part. Here we all the solution we do actually for this part. We find The value of this is actually have two possibilities, either 0 or 1, depending on whether k equal to 1 or k equal to L or not. So let us put all these results here, this equation. So let us write the whole combination of this equation. Okay, so let us write the whole equation, which is actually let me see. Let me write this equation. Did we already give it a name? Okay, so I'm writing it with this combination. Okay, let's see. We already give it a name or something. Yeah, xt. When we write xt, then what is the xt comes? Oh yeah, we already took a periodic signal xt. So what we can write? Oh, okay, let us write only this portion first. Let us solve this portion first, or fill up this equation. This one, coefficient. This is for the coefficient. We can write that 1 by t minus t by 2, 2t by 2 xt is the power minus j twice by L, L is 0t dt, which we actually write as a, like we put the xt value, which is k equal to minus infinity to plus infinity. At the beginning, we actually try to, when we are solving this equation, we actually write by this equation. So I'm writing it again. So minus infinity by 2 to t by 2 for one period is the power j 2 pi k minus L 0t dt. Here we know the value. For example, we already know the value of this one. Value of this one. So what is the complete value? Now we actually write the whole one. What is this value? If this becomes 0, the whole equation becomes this one, whole becomes 0, right? Okay. So this is actually 0. Its value is 0 if k equal to not equal to L, and its value becomes 1 if k equal to L. Where we can write that, okay, this value varies. This is the variable where this value depends on this 0 and 1 value. So we can actually easily sum it as k equal to minus infinity to infinity ck. This whole portion we can actually write as is del of k minus L. You see here del 0, if it is 0, del 0 is 1. When del 0, when k is not equal to 1. So k equal to L, this becomes del 0. If this is the k equal to 1, k equal to L, then it becomes del 0. So del 0 is 1, or del of, for example, n, which is actually 0. N means, what is this n? N is the any other integer. Here n value is any other. Any other integer. Except this L, any other integer. So this equation we can solve it. This is equivalent to, we can give it a name, C of L. This is actually CL, which is actually the coefficient of the Lth harmonics. This is actually nothing but the coefficient of Lth harmonic. And it actually, otherwise it's actually Lth coefficient, or if we like abbreviate is long, that we can actually term that as the Lth coefficient of the discrete Fourier series representation of the period signal xt. So we other way we can also write it. This is actually a Lth coefficient of discrete Fourier series representation of the periodic signal xt. So which is actually ultimately this is actually expressed by CL. CL is a coefficient of the Lth harmonic. Okay, so means actually by using CK, where CK was the any harmonic from minus infinity or this value K is minus infinity to infinity, we can actually specify a specific harmonic. Okay, so in this chapter we actually, or in this lecture we actually came to know that any periodic signal which is actually applicable for a discrete or they are discrete in frequency, for any periodic signal we use a Fourier series where we can say that a Fourier series of a periodic signal is nothing but the the linear combination of a complex conjugate or complex sinusoids of its harmonics. And these harmonics, and every harmonics will be represented by a coefficient. And for a specific coefficient or Lth, for example, in our case, a specific coefficient, this value, Lth coefficient is this. Means for any harmonics, this is the coefficient. So once we know a coefficient value, CL, we can also know this specific value, right? This specific value, for example, in our case, for the signal xt, if you want to know its harmonic, so you know what is its Lth value and Lth complex sinusoids. So you can actually know the Lth harmonics. And this X is Fourier series nothing but the combination of those harmonics. So we can express any periodic signal by its harmonics, by a series of linear combination of harmonics, and we know the individual, or we can find the individual complex sinusoids and Lth or that coefficient of that harmonics. So which will be the series of. So by adding all these series, we can actually express this X for its fundamental frequencies x1, x2, x3. Okay, so here ends actually our lecture today. Assalamu alaikum.